Well, we made it. This is the last lesson of the year, and wrap up our unit on financial applications. So we're going to talk about annuities and sort of looking at it from a different perspective. So at the very beginning of this unit, I kind of looked at the value of money. Really, that's what this whole lesson is about: the value of money or the value of an investment. And there's two perspectives that we could look at, either whether it's the present value, in other words, how much is that investment worth now, or how much I have to put in now, and the future value. In other words, how much is that investment worth in the future, or how much is it that I need in the future. So let's start with a warm up. Brad will be starting university in 4 years, and he wants to start saving for a car so he could drive around on campus. So here are some important information. It's 4 years. He wants to have $10,000 by the time he starts university. He found an investment that will pay him 2% per annum, compounded quarterly. How much does he need now in order to achieve his financial goal? So how much does he need now? So we're talking about present value, and we're assuming here that it's just a one-time investment. So this is just going to be a compound interest formula. So that again is future value is equal to the present value times 1 plus I to the power of n. So before we start going off and plugging numbers in this equation, solving for it, we have to determine what we're given. So first thing is we're given years, so that's time is 4 years. He wants to have $10,000 by the time he starts university, so that's going to be his future value is $10,000. It's paying him 2%, so investment is paying 2% per annum, so that's the rate is 0.026. And then finally, that's compounded quarterly. So there, my compounding period was 4. So from there, now we could derive some other variables such as n. So n again was c times t. So the number of compound periods is 4, and the number of years happens to be 4. So there's going to be a total of 16 interest payments. And what's the interest on each of these payments? So that's I. That's going to be 0.026 divided by 4, which is, take out our calculators, 0.06 0.0065. So that's the actual interest rate each time. So we just go plug that into our equation now. 10,000 is equal to the present value, which we're trying to figure out. 1 plus, I'm going to do this all together. So 1 plus 0.0065 is 1.0065, all to the power of n, which is 16. So here we can sort of shortcut this, or not shortcut this, isolate for PV. So present value is going to be 1,000 times 1.0065 to the power 16. So it's important that we plug this in all into our calculator at once. And when we do that, we discover that the answer is, so over here, present value is $9,015.29. So this is how much Brad has to put in now. So he has $10,000 in 4 years. So unfortunately, Brad does not have that much money up front. So if he was to save quarterly into this investment, how much does he have to put in every 3 months? So because now he's going to be putting in some money on a regular basis, that's the definition of an annuity. And because the amount, the period that he's putting in every 3 months happens to match the investment that he's getting, which is paying him interest every 3 months or quarterly, that's the idea of a simple annuity. So we just pull our simple annuity formula, which is future value is equal to R times 1 plus I to the power of n minus 1 all over I. So all our variables still stay the same, except just we're using a different formula now. So future value is 10,000. We don't know what R is because that's what we're calculating for. So this is going to be 1 times, I'm going to do 1 plus I together, so it's going to be 1.0065, and it's still 16 to the power of 16 minus 1 over 0.0065. So here we could sort of multiply both sides by 0.0065. So here we can get 65 is equal to R times 1.0065 to the power of 60 minus 1. And really, so R is 65 divided by 1.0065 to the power of 16 minus 1 as a denominator. And plugging that in our calculator again all at once, we discovered that Brad is going to have to make regular payments every 3 months of $595.09. Okay, which is a lot more practical, a lot more feasible, as opposed to getting up $9,000 up front. So today we're going to talk about the present value of annuity. So first of all, I'm going to introduce what that concept is. What does that mean? But before we get there, we're going to rely on our compound interest formula again, but from a different perspective. So here, a regular compound interest formula was future value is equal to present value plus times 1 plus I to the power of n. So when we want to calculate for the present value, which is what we did in our example, really we could say, one way of saying this is that the present value is future value divided by 1 plus I to the power of n. In other words, we're going to divide both sides times 1 plus I to the power of n. Another way that so we could create this equation is using our our knowledge of exponents. So instead of writing our denominator as 1 plus I to the power of n, we could say that this is the same thing as future value of 1 plus I to the power of negative n. Okay, so again, they kind of mean the same thing. In this case, it's just kind of a little bit easier to write because we sort of keep everything on one line. It's not a fraction. If you have a calculator that actually deals with exponents, can handle negative exponents, this is another way to sort of plug that into your calculator, remembering to put 1 plus I first, or do that in brackets before taking it to the power of n. So the power of negative n. So let's look at a future annuity. So the present value of annuity, and here's an example. Before we get to the example, let's do some definitions. So I'm going to show this with a timeline to calculate the present value. And again, the only type of annuities that we do are simple. In other words, they match the payments that are going in. The regular payments match the investment or the compound interest payment as well. And ordinary means that they're being done at the end of that payment. Calculate the present value of an annuity with a formula. So once I give you the formula, it's really just memorizing that formula and doing the various algebra to get the different parts of that formula. Okay, so here's an example. Richard bought a PS4 bundle that included free online gaming for a year. So he was disappointed when PS3 came out. It was free online gaming, but now with PS4, you actually had to pay, well, this time when I created the example, $50 a year. I'm not sure what it is now, but we'll keep it as $50 for a PlayStation Plus account to keep playing online with friends. So because he learned financial math, he decided to mitigate his costs through investing. So he wants to be able to play his PS4 for the next 20 years. So in order to pay for his online game for the next 20 years, he wants to he wants to invest something now so that he can get a regular payment from that investment. So the idea here is that if he plays 20 years and he just does as normally, pays $50 every single time out of his pocket, if you want to call it that, he's going to pay $1,000, 20 times 50. So the idea here is that instead of kind of weighing each time and paying that up front, paying at the time, we can make a deposit now of a certain amount and then let that amount grow with investments, but taking out money at a regular interval. So that the idea is that we put some money in, we're going to let interest grow that investment in there, but knowing that from time to time, in this case a regular period of time, we're taking money out of that investment to do what it is that we want to do. So in this case, pay off to pay for Richard to pay his for Richard to play online on his PS4. So how can we sort of show this on a timeline? So here's our timeline. Again, I'm going to shortcut it because we don't want to do everything. So here we're going to start time 0, maybe at 1 year, 2 years. We're going to go, so after 20 years, and let's do 18, and maybe we'll add another one in here, 3, just to see what's going on. So here we want to think, what is the money that we need now? And in the future, we're taking out $50. So instead of paying $50, and so to speak, we're actually taking out $50 from our investment. So by the very end, by this last payment, when we take out $50, the idea is that we have nothing left in this account. In other words, we did the math exactly. We put an amount now, and 20 years later, at that last $50 I take out pays for my last year playing on my PS4, and I should have nothing left in this account. Well, we sort of have to work backwards. Okay, so because we want to know how much money we need to put in now. So in this case here, again, I'm going to write a formula that we just did for compound interest, was present value is equal to future value times 1 plus I to the power of negative n. So in this case, because we have to wait for, we only earn interest once on this $50 that we're taking out later on. What's the value that we put in now? So the present value in this case is going to be 50 times 1 plus, I didn't calculate the interest rate. So here we got 3.75, so that's R is 0.0375, and pays them compounded annually, so that's also I, because there's only one interest payment per year. So in this case, it's going to be 1 plus 0.375, and so let's just add that together. So it's really 50 times 1.0375. So whatever that amount is, he has to put that in. And 1 year from now, he'll have $50. So we kind of have to keep working backwards. Oops, extended that too long. In this case here, we got present value is equal to $50. And here we're going to be 1.0375. In this case, we're going to have to wait 2 interest payments. So that's going to be -2 to the power of -2. I forgot the exponent in the first one. And finally, the third one here, we're going to say that the present value of this payment that we need to do to get $50 3 years from now is 50 times 1.0375 to the power of -3. And we're going to see that this pattern continues. So let's take 18 years from now. How much does he have to invest now to get $50? So that is going to be present value is equal to 50 times 1.0375 to the power of -18, because we're actually going to get 18 interest payments on it. And the pattern continues. So their present value is 50 times 1.0375. I think I forgot a 7 up here. So 7.5. In this case, the power of -19. And finally, this last one, present value is equal to 50 times 1.0375. Keep missing the 7. To the power of -20. So here we can see that this is just going to be another geometric ratio. So go off and sort of go back and look at our equation for a geometric series. So S of n is a times r to the power of n minus 1 all over r minus 1. So that was a little bit tricky equation. So let's go back and look at the pattern that we established. So the very first payment, first number in our series is actually that. What's the ratio? Well, the ratio is, so we're dividing by 1.0375 every single time. So R in this case is going to be 1.0375 to the power of -1, or 1 over 1.0375. So let's go off and plug that in. So A is 50 times 1.0375 to the power of minus 1. Our ratio here again was going to be 1.0375. So to the negative 1 times to the power of n, that's going to be to the power of negative n minus 1. So all that in brackets. And finally here, the ratio here, denominator is going to be 1.0375 to the power of negative 1 minus 1. So we plug that onto the calculator. You kind of need to be careful doing this way. Might want to do several steps. But at the very end, Richard needs to put in $694.81. So not bad. Instead of paying $1,000 over a period of time of his money, he only in this case needs to put in really at the start $695, which is over $300 savings. And over that time, he could play his PS4 for 20 years, taking out $50 every single year. So that's the idea of annuity and how we calculate for the present value. In other words, how much money that we want to put in now, and then we take out money at a regular period in order to pay for something or in order to do something. So again, think of the reverse is this is what happens when we take out a loan. We take out a loan and we're going to take out present value now. In other words, we can only afford to pay, let's say, $50 a month, $100 a month. So how much of a loan can we afford to take out now? So sort of the opposite effect, so that at the very end we could be able to pay off this loan. So that's another perspective that we can kind of see on this. So instead of doing that big formula at the top, we could really simplify this formula into this. So again, it's a little bit tricky. So here the present value is equal to that regular payment. And then we need to do 1 minus, in brackets, 1 plus I to the power negative n. And then dividing all that by I in order to get the present value. And multiply by R afterwards to get our present value. So here, so again, that's what those variables mean. And they don't mean any different than in our future values for an annuity. So let's go back to that example of me still trying to get my Porsche. So I decided that I want my Porsche now, so I'm going to get a loan. So I found a loan that pays me 4.5% per annum, compounded monthly. And if I want to pay off my loan in 25 years, what will my monthly payment be? And more importantly, then this is the power or the unfortunate thing about interest is that really that affects our overall cost of something, because now I'm impatient. I want that money now. I don't have that money now. I'm going to borrow that money. There's a price for paying for borrowing that money. So here, this is the idea of really a present value of an annuity. So again, our equation is present value is equal to R times 1 minus 1 plus I to the power of negative n all over I. So let's go off and deduce what is it that we have. So $250,000. So that's my present value. That's how much is that investment worth now, or that Porsche, or how much money I need now. So that's present value is $250,000. Charges me 4.5% compounded per annum. So there's my interest rate. R is 0.045. Compounding period, so I actually did really well. I found something, well, not really well. I mean, that's how banks usually charge. They charge you on a regular basis. The best you could probably do is compound it monthly, but probably it's going to be something that compounded every 2 weeks, every week, or worse comes to worse. That's what credit cards do. They charge you interest every day. So here, compounding period is 12. So here, and the time again is 25 years. So from there, I can say that n is going to be 12 times 25. In other words, this is the number of interest payments I have to do. I'm charged. So 12 times 25 is going to be 300. And then I is going to be 0.045 divided by 12, which is, plug that into our calculators, 0.045 divided by 12, and we get 0.00375. So we need to be exact with the interest rate as well. And now it's just an exercise in our calculators. So we need to say present value is equal to R times 1 minus 1.00375 to the power of negative, in this case n is 300, so negative 300 all over 0.00375. Should replace, let me do that, present value with 250,000. So 250,000 times 0.00375 is 937.5 is equal to R times 1 minus 1.00375. I keep forgetting 7 for some reason. To the power of negative 300. So it's important that we do that calculation first before subtracting it from 1. So really we just isolate for R. So R is going to be 937.5 divided by 1 minus 1.00375 to the power of negative 300. Again, doing that on my calculator, I'm going to discover that I need to make a monthly payment of approximately $1,300.89. Sorry, $1,389.58. So that's a pretty big chunk of change, big monthly payment I need to do, only because I want that money up front and it's going to take me a very long time. And again, that's where the negative 300 indicates a lot of interest payments on that $250,000 initially took out. So that's what I have to pay every month. So approximately almost $1,400. So how much did I actually pay for my Porsche? Well, the cost of the Porsche, really out of pocket for me. I bought it for $250,000, but what I wound up paying, I spelled that, I'm sure. No, I got it. Cost of Porsche is really $1,300, or really let's round up $1,400 times. I make 300 payments. So 1,400 times 300, $420,000. So that's the cost of having something now, borrowing some money, using somebody else's money, paying to use that money, and then I pay really $420,000 for that Porsche. Pretty expensive. So the last example I want to do is sort of tying in the two things. And this is probably the most practical example, and in some ways the most complicated example, but it's really combining the idea of a future annuity and a present value annuity. So I want to retire early in 20 years. I calculate that I will need $5,000 a month after I retire for about 10 years. So I'm working for 20 years. And then in 20 years' time, I'm going to retire. And at that time, I know I'm going to need $5,000 a month after I retire. And how much I need that money for that $5,000 a month is I need that for 10 years before my pension starts. So after that, I can withdraw for my pension. And then I don't need the savings anymore. So if I lock into an investment for the next 30 years, and the 30 years is 20 plus 10, that pays me 3.6 per annum percent compounded monthly. And this annuity will actually allow me to convert it. So basically the first 20 years I'm putting into it, so I'm building up interest, and then after 20 years it's going to allow me to sort of stop investing but take it out, but still continue earning 3.6% per annum on whatever money that is still in there until I take it all out. So we need to sort of have a different picture of this. So here we have sort of now, the next time frame that we're given is 20 years from now. And then 20 years, or then 10 years later, which makes it 30 years from now, I'm going to retire. Sorry, I'm going to keep drawing and I'm not going to need this annuity anymore. So this is my retirement. And this is when I've withdrawn all my money. So we need to look at this from two different perspectives. Is how much, so within each of these, and I should have broken up this line. So two blips in time. So each time I'm going to have $5,000. And same thing with this timeline in order to save me for it, but in this case, I don't know how much I have to put in every month in this case to save up 20 years from now so I could withdraw $5,000 every month for the next 10 years. So that's really the problem that we're facing. So really, it's a little bit of a game of back to the future or jumping into time. So really, we want to jump 20 years into the future and say, well, what is this value that I need now at that time, 20 years from now, so that I can keep withdrawing $5,000. So really, we want to jump into the future and look at that as the present value. What's the present value of this lump sum that I need so that I can withdraw $5,000 every month for the next 10 years? So let's go off and plug in some variables that we need. So one thing that's consistent for everything is my 3% per annum. So R is 0.036, and because I'm paid this monthly, so C is 12. So those things are consistent for the entire 30 years. In this case, I is equal to 0.036 divided by 12, which is 0.003. Well, looking at this point 20 years from now, how many payments do I need? So here T is going to be 10. So let me do this in a different color. So let's say that this portion is the purple. And here T is 10. So what does that make N? So N is going to be 10 times 12, which is 120. My I is still 0.003. In this case, my regular payment is 5,000, or regular withdrawal that I'm taking, that regular amount. So here we have to go off and calculate our present value is, so what was our present value formula? Present value is equal to R times 1 minus 1 plus I to the power of negative n all over I. So present value here is going to be 5,000 times 1 minus 1.003 to the power of negative 120 all over 0.003. So we carefully plug that into the calculator. We discover that, so 20 years from now, what I need to have in my investment is $503,000. It's $503,245.97. Okay, so sort of jumping into the future 20 years from now, this is how much money I need now, 503,000 and change, so that for the next 10 years I could withdraw $5,000 exactly, and by the end of that 10 years I will have no money left in my investment, which is fine. I can use my pension. So here we got our present value was there. So we got to jump back to the present. So now that present value is really something in the future. What's the future value of my investment that needs to be in this case? $503,000 and change. So how much do I need to regularly invest now on a monthly basis? So here we need our future values equation. So here we're calculating for this part now, which I've done in green. So here we need to, so this present value turns into a future value when we're back at this starting timeline now. So in this case, N is, sorry, let's do T first. So T in this case is 20 years. So that means N is going to be 20 times 12, which is 240. I still stays the same. And my future value in this case is this amount here. So what's our present value annuity formula? So digging back in, we recognize that, oops, not present value. Future value is equal to R times 1 plus I to the power of N. So all that minus 1 divided by I. So let's carefully plug this in. So here my future value is $503,245.97 is equal to R times 1.003, in this case to the power of 240, minus 1 all over 0.003. And if I'm just going to shortcut this, plug that in carefully in the calculator, isolating for R, we're going to discover that I need a monthly payment of $1,434.81. So that means starting now, I need to invest approximately $1,434 or $35 every month for the next 20 years. So that by that time, I will have over $500,000 saved, and then I could withdraw $5,000. So actually, a regular payment every month of $1,435 is really expensive. That's a lot of money. You'll be lucky to earn maybe a few $1,000s a month before taxes. So that's a big chunk of change. And this is why investing early, start to think about your retirement early, makes a big difference. So one thing that we could say from your perspective, if let's say that you want to retire early, or you want to start saving now for retirement, and you retire 50 years from now. So we sort of have the same idea that 50 years from now, you want to withdraw $5,000 every single time. And what would that, how much money would you need then? So we actually replace, in this case, T for 20, instead of 20, is actually 50 years from now. We're going to discover that you only need to put in $300 approximately. So that's a huge difference. Sorry, that number I got for 300 is if you want to retire 40 years from now. So here you're young, you're 16, 17, what it is, 40 years from now. So what's going to happen is that if you invest early, you only need approximately $300. So that's a big difference that we're sort of accounting for here. Okay. So that's it. If you want to practice some of these things, there's the homework, but that's the end of our financial unit. And hopefully, while we see that some of the situations we really simplified, made various assumptions, once you get in the real world, there's going to be various amounts of different financial situations or circumstances that could exist. And that's why, the area of financial math is pretty popular, but also pretty complicated due to different options that are out there.